Hey there guys, welcome back to another video. Today we are going to be introducing you guys to the idea of differentiation. And we're going to start very basic with differentiating polynomials. And let me first say that there are a few notations that I want you to get to know. So the first one is f prime of x is equal to the derivative of y in terms of x. So you'll see both of these throughout my videos, and let's start with this actually by defining when to use them. So as you can see, we have f of x is equal to x to the power of n. In the case of finding the derivative of this, you'd go f prime, use this definition, is equal to the derivative of this, which we'll go through soon. And if you see y is equal to x to n, then you just put dy dx is equal to x, whatever the derivative of x to n is, which we'll get into in a minute. And that is saying the rate of change in terms of x. So the rate of change of y in terms of x. Okay, so let's get started with the example here. So we have f of x is equal to the x to the power of n. And let me just go ahead and state the rule right now. F prime of x is equal to n multiplied by x to the power of n minus 1. So as you can see, n multiplied by x to n minus 1 is the derivative of f of x. So basically what we're doing is we're taking some constant n, multiplying it out front, and then just reducing n by 1. So this is what we call the power rule. And if you've had experience with calculus before, then you likely know this. Well, you definitely notice if you've differentiated polynomials before. And later on we'll talk about a rule called the chain rule, which I won't get into right now, but it basically uses that same idea. So should we do a few examples? Let's say, for example, n is equal to 3. So f of x is equal to x to the power of 3. The derivative here would quite simply, using our definition here, would be 3 multiplied by x to the power of 2, which is the same as 3 minus 1. So just using our definition there, which is equal to 3 to the x squared. Okay, so that is the same there. And let me go ahead and put a bit of a more subtle example. F of x is equal to a to the power of a multiplied by x to the power of 4. Now here, a is what we call a constant. So we'll have a constant value, such as 2, 3, 4, 5, 6. It's not changing. So we do not have to differentiate it. If it wasn't a constant, such as y, then we'd use something called the implicit differentiation rule, which we'll get into in a few videos' time when we get onto the chain rule. So the derivative of this is 4a x to the power of 4 minus 1, because our n is 4 in this case, and our n minus 1 can simplify to 4ax to the power of 3. So 4ax cubed. Okay? And that is the power rule. So it's a pretty simple rule. Let's say, though, I have a string, like a polynomial. F of x is equal to 4x squared minus x plus 1. Okay, so this is going to give us a new concept here as well, so take note of this. F prime of x is equal to 8x minus 1, okay, and plus 0. Now you might be thinking, does that mean 1 differentiates to 0? The answer is yes. So just like a, 1 is constant. If we take the derivative of it, we're finding the rate of change of y in terms of x, or in this case f of x in terms of x. So basically, it has no change in respect to x. It's always 1. So the derivative is 0. Okay? So dx, so this is saying the derivative of the following thing, of 1, is 0. Okay, so that's basically what we're stating right here. And of course, we've got the string. So a linear combination of any differential functions is always like this. They're independent of one another. Okay? So let's say I have ax squared plus bx plus c. If you don't know what this is the set for a quadratic equation, the formula you could say. So f prime of x in this case would be 2ax plus b. Okay? So linear combinations of polynomials are always independent to one another. Okay? So in the next video, we'll take a look at some more complex examples.